Hey everyone, welcome back. Today we're diving into one of the most interesting architectural ideas to come out of AI research in the past year, recursive language models. This is the idea that instead of stuffing more text into a model's attention window, you let the model write code to explore its own data. And it turns out that's a much more powerful approach than it might sound. Let's start with the problem. Transformer-based language models have a fundamental constraint. Their attention mechanism scales quadratically with input length. That means doubling the context makes it 4 times more expensive and slower to process. And even if you make the window bigger, you run into something called context rot. The model's ability to actually use all that information degrades long before the window is full. Studies have shown that models with 200,000 token windows start losing coherence around 130,000 tokens. Not gradually, but abruptly. The workarounds people have tried, text chunking, summarization, retrieval augmented generation, all come with significant trade-offs. Chunking destroys the semantic connections between sections. Summarization loses fine-grained details that might matter later. And stuffing retrieved passages back into the context just recreates the same crowding problem. What none of these approaches do is let the model itself decide how to explore the document. That's exactly what recursive language models do. The paper was published on December 31, 2025, by researchers at MIT, Alex Zhang, Tim Kraska, and Omar Khattab. The core idea is to move the document outside the model entirely. Instead of loading a massive text corpus into the attention window, you put it into a Python variable in an external REPL environment, a read-eval print loop, which is just a sandboxed coding environment. The model never sees the raw text directly. What it sees is a description of the environment and a user query. Then the model does something clever. It writes Python code to explore the data. It might start by checking the length of the document, then look at the first few hundred characters, then search for specific keywords with a regular expression. When it decides it needs to semantically analyze a particular chunk, not just find it, but understand it, it calls a special function called LLM_query, which spins up a new submodel in a fresh sandbox to handle just that piece. The result comes back not as raw text dumped into the main context, but as a Python variable. The main model's context window stays clean. This architecture has some important advantages over standard language models. First, exact computations. If you ask a normal model how many times a certain word appears across a 100,000-word document, it will often give you a wrong answer because it's estimating statistically. An RLM just runs the regex and counts. It cannot hallucinate that result. Second, the model can handle effectively unlimited input. 1 million tokens, 10 million, doesn't matter, because the raw data never enters the attention window. Third, the cost per query can actually be lower because you're using cheap symbolic operations for most of the work and only calling an LLM when you actually need language understanding. How does it compare to recurrent models like Mamba or RWKV? Those architectures tried to solve the context problem by replacing the quadratic attention mechanism with a linear one, compressing information into a fixed-size hidden state as they read through the input sequentially. The problem is that compression necessarily loses information. Complex logical structures can't be perfectly preserved in a finite hidden state vector. RLMs take the opposite approach. They never compress the data at all. The original document stays intact in external memory, and the model accesses it through code with random access, meaning it can re-examine anything it's already seen. Now let's look at what happened after the original paper. By mid-2026, researchers had started building systems that take the recursive idea further. The most striking result is RLM-QN38B, a model with only 8 billion parameters that was specifically fine-tuned to use the RLM framework natively. Most language models are trained to produce final answers, not to iteratively explore data through code. This model was trained to do exactly that, and the results were striking. It outperformed the base QN38B model by an average of 28.3% on long context tasks, and in some benchmarks matched or exceeded much larger vanilla models. Another application showed up in an unexpected domain: pharmaceutical modeling. A system called PKGPT used the RLM approach to automate a type of drug analysis called population pharmacokinetics modeling. This involves fitting complex nonlinear equations to patient data using specialized software called NONMEM, which has a very rigid and unforgiving syntax. Previous LLM attempts would generate code that immediately crashed. PKGPT's approach was to run the code, read the error log, pass that back to the model, and repeat up to 20 times per stage across 5 stages of analysis. It's the RLM pattern exactly. Execute, observe results, adjust. In testing on the antibiotic tobramycin, PKGPT actually achieved a better statistical fit than human experts, though with some parameter estimates that were physiologically implausible, which is an important caveat. But here's where it gets complicated. A paper published in March 2026, titled Think, but Don't Overthink, tested what happens when you increase the recursion depth beyond one level. At depth 1, the root model spawns submodels to handle chunks of the document. At depth 2, each of those submodels can spawn their own submodels. Researchers tested this on DeepSeek version 3.2 and Kimi K2 and found a paradox. On a complex multi-document reasoning task, depth 1 improved accuracy from 0 to 42%. But depth 2 dropped it back to 34%. Meanwhile, the cost exploded, from around 25,000 tokens per query at depth 1 to about 2.5 million tokens per query at depth 2, with latency going from 3.6 seconds to over 5 minutes. The reason for the performance drop is that models don't yet know when to stop recursing. At depth 2, you can end up with over 100 submodel calls, many of them redundant. The models fall into what the paper calls an overthinking state, checking the same data over and over, generating intermediate outputs that don't contribute to the final answer, and eventually corrupting the output format entirely. This suggests that native RLM training, teaching the model when recursion is actually useful, is critical before depth can be increased. So how should you think about implementing this? The practical guidance from the original paper breaks down into 5 principles. First, explore before you analyze. Start with quick peeks at the data structure before diving into heavy computation. Second, work in small steps. Don't try to solve everything in one code block. Third, use code for finding things and submodels for understanding things. Fourth, don't retype data. When you find a value, store it in a variable and reference that variable later. Don't copy-paste it into text. And fifth, monitor what's happening. The framework includes logging tools so you can see the full execution trace and tune accordingly. One important practical consideration: the current RLM architecture is blocking. Each submodel call has to finish before the root model continues. That makes it poorly suited for real-time conversational applications. Where it shines is in asynchronous, batch-style work, deep research tasks, large document analysis, complex report generation. Think of it less as a chatbot enhancement and more as an analytical engine you run over large corpora. The big picture takeaway is this: recursive LLMs represent a shift in how we think about scaling AI capability. For years, the assumption has been that bigger models and longer context windows are how you get smarter systems. RLMs suggest a different axis entirely. Let the model interact symbolically with its environment, recurse into subproblems, and use code as a first-class reasoning tool. A model that knows how to explore data intelligently can outperform a model 10 times its size that just reads everything at once. That's it for today. See you in the next one.